Okay, welcome to the next video. The first three videos covered off specification reference 3.4.1, and this video on the equilibrium constant starts us off on specification reference 3.4.2. So what we're going to learn today is we're going to learn that Kc is the equilibrium constant as opposed to the rate constant. The rate constant with a small k, this is a big K with a suffix c, and it's calculated from the equilibrium concentrations for a system at constant temperature. And we want also to be able to construct an expression for Kc for a homogeneous system in equilibrium and perform calculations involving such expressions. Let's start by recapping equilibrium, and I like to recap equilibrium with three charts. And the first chart, let's draw a little graph of concentration versus time. So if we have a reactant A, and let's say that's going to start and then react and then stop changing at this point. We could also consider a reactant B, or a product B rather, and that could start at 0 and the amount would increase, but increase at a decreasing rate until it also stops increasing and there's a steady amount at equilibrium. And so what we can say is that at this point of time here, this is where we reached equilibrium because the concentrations of reactants and products have changed. So just for the avoidance of doubt, we've got an equilibrium situation like this where A is the reactant and B is the product. And when their concentrations have stopped changing, that's when we're at equilibrium. We could also draw a similar equilibrium, also concentration against time. However, in this case, we would have A would decrease less and B could possibly increase less as well. So in this case, this is concentration of B, and the top line is concentration of A in the same reaction. And this is also in equilibrium, so the concentrations don't have to be the same, they just have to have stopped increasing. And so at this point in time here, when the curves have flattened out, that's when we've got equilibrium. As a point of interest, one of these charts is going to signify a situation where the yield of B is high, and one of these charts is going to signify a reaction where the yield of B, the products, is low. I'm going to give you 10 seconds to work out which is which. Hopefully you've done that, and so in this case we have yield of B. In this case yield of B is low, and in this case the yield of B would be high. Okay, now we can also look at equilibrium in another way by drawing a chart of rate against time. And we can consider the rate of with respect to the reactant A, and at the start, reactant A, the rate is going to be high, and then it's going to decrease as it gets used up, and then it's going to flatten off as it reaches equilibrium. And also we can consider the rate with respect to B, Now at the start there's no B, right? And you would start increasing B, and when the rates are the same, that's when we've got equilibrium. So the equilibrium is reached here when the forward reaction is equal to the backward reaction. Forward rate equals backward rate. So equilibrium is reached either when the concentrations of reactants and products are no longer changing, or the forward rate is equivalent to the backward rate. Okay, let's get on to the equilibrium constant, Kc. Now, the equilibrium constant is best described if we look at a general reaction, which I'll write here. So let's have small a plus small b, b, and that's in equilibrium. They're the reactants. That's in equilibrium with two products, d moles of D plus E moles of E. So the small lowercase letters just signify the moles of each reactant or product in the balanced equation. And A and B are the two reactants, and D and E are the two products. And if we consider that generic reaction, then let's write an expression for the equilibrium constant. All right, so the equilibrium constant, capital Kc, compares the concentrations of the products to the concentrations of the reactants, and it's a ratio. Okay, so we're going to take concentration, you remember that square brackets, of D, and that's to the power of the number of moles of D in the balanced equation. So we put a small d here. And the other product is E, so we take the concentration of that at equilibrium to the power of E, small e, that's just a number of moles of E in the balanced equation. And it is that over the concentration of A to the power of the number of moles of A times the concentration of B at equilibrium again to the power of the number of moles of B. And that is the expression for the equilibrium concentration. So notice that on the top of on the numerator of the ratio we have the products, and on the denominator we find the reactants. And that's true for one particular temperature, and at a different temperature you will have a different value of the equilibrium constant. So that's the generic equation. Let's have now a look at an example of a real equilibrium reaction. So if we consider this reaction with hydrogen gas reacting with iodine, let's say it's also a gas at this temperature, that's going to be in equilibrium with 2 moles of hydrogen iodide, and that is also a gas. So the forward reaction is the reaction where hydrogen reacts with iodine to produce hydrogen iodide, and that's going in the direction left to right, the forward reaction. But at the same time, the backward reaction is happening, and that's when hydrogen iodide decomposes back into its constituents, hydrogen gas and iodine gas. Both happen at the same time, and in a closed reaction vessel there will be all of hydrogen gas, iodine gas and hydrogen iodide gas, and the concentrations of each will be constant at equilibrium because the forward reaction is happening at the same rate as the backward reaction. So let's write the expression for Kc here using the generic equation on the left. So we've got Kc equals, we take the product, in this case there's only one product, and that's hydrogen iodide. All right, so we want the concentration of that at equilibrium, and notice there are 2 moles in the balanced equation, so we square that, and that's going to be divided by the concentrations of the reactants. So first reaction is hydrogen gas, and that is to the power of 1 because there is 1 mole of hydrogen in the balanced equation, and we also have iodine as another reactant, and there is also 1 mole of iodine in the balanced equation, so that is to the power of 1. And of course you remember from the previous section that if the power is 1 we can avoid writing it just for brevity. So we could rewrite this equation, concentration of hydrogen iodide squared divided by the concentration of hydrogen times the concentration of iodine. And there is the equilibrium equation expression for that particular equilibrium reaction. One further point to make about the powers involved in the expression for the equilibrium constant is that they are nothing to do with the orders of the reaction in the rate equation. These powers here are the moles from the balanced equation, whereas the powers, you'll remember from the rate expression, are the number of molecules of the species that happen to be in the rate determining step. Quite different, don't confuse. So questions on the equilibrium constant take 2 forms. One is that you are given the molar concentrations, or in fact you might have to work out the molar concentrations, and you have to find Kc, the equilibrium constant. And the other type of question you get is when you have to work out the concentrations from the equilibrium constant. So first thing first, let's calculate Kc from concentrations. Let's stick with the hydrogen iodide example, and this particular question has equilibrium concentrations at hydrogen iodide, the product, it's 0.80 moles per decimeter cubed, hydrogen gas at 0.10 moles per decimeter cubed, and iodine, the other reactant, at 0.1 also moles per decimeter cubed. Notice they give you a temperature in Kelvin, and the fact that it's 640 Kelvin doesn't matter. All they're saying there is that the temperature is constant, and so you don't need to worry about it. Okay, so the question is, what is the equilibrium constant for this reaction at that temperature? Now, we worked out before the expression for Kc. Let's just remind ourselves what it is. Capital Kc equals, and it was the product hydrogen iodide, product concentration at equilibrium, all right, to the power of 2, so 2 moles, and that was on top, and then we had the hydrogen concentration just to the power of 1, and the iodine concentration also to the power of 1. That was our equilibrium expression, and all we have to do is we have to feed in the concentrations that were given in the question. So as you can see, the concentration at equilibrium, notice it says equilibrium concentrations. So at equilibrium there is 0.8 molar hydrogen iodide. So let's put in 0.8, that's going to be squared, divided by hydrogen concentration is 0.1 times iodine concentration also 0.1. And when you feed that into your calculator, you're going to get 64. However, 64 what? We do need to put the units in, and just like in the rate expression, the units can change. So in order to calculate the units, then all we do is we put the units into the expression for equilibrium constant. So Kc equals, concentration of hydrogen iodide squared. So concentration is always mole dm minus 3, and in this case that's all squared, and that will be divided by the concentration of hydrogen, which is also mole dm minus 3, times the concentration of iodine, which is also mole dm minus 3. Okay, so as you can see, they will all cancel out. So you've got 2 mole per dm cubed on top and 2 on the bottom. All right, so they cancel out, and in this case, Kc has no units, and the answer is just 64. And that would always be true when the number of moles of reactants equals the number of moles of products. That's not always the case though, and when it isn't the case, then Kc does have units. Okay, so it's not often you get a question quite so easy as the previous one. Normally we have to work out some molar concentrations before you can put the concentrations into the equilibrium expression, and this is one such question here. So we have 0.2 moles of phosphorus 5-chloride decomposing at 600 K in a vessel of 5 decimeters cubed. So the equilibrium mixture is found to contain 0.08 moles of chlorine, and the question wants you to write an expression for Kc and calculate its value including units. So let's go ahead and do that. First of all, let's write down the balanced equation. And the balanced equation starts off with the phosphorus 5-chloride. So if it's phosphorus 5, it's going to have 5 chlorides attached to it, and that's going to be in equilibrium with chlorine gas, Cl2. And if Cl2 has decomposed off, then the remaining part of the molecule is going to be phosphorus trichloride. So they are our 2 products that have decomposed, and we started off with phosphorus pentachloride. So that's a good start, and our equilibrium expression is going to involve all 3 of those. So if we make a capital K, right, we're going to have the concentration of phosphorus trichloride times the concentration of chlorine divided by the concentration of phosphorus pentachloride, all to the powers of 1, because there's 1 mole of each. So there we have the expression, but at the moment we have no concentrations. The only 2 things that we have to go on so far are 0.08 moles of chlorine at equilibrium, and before equilibrium at the start we have 0.2 moles of phosphorus chloride. So notice we've got moles and not concentrations, but that's fine. Let's work out the concentrations from the moles. First of all, the moles. Okay, we're told we have 0.08 moles of chlorine. So let's have a look at what happens to phosphorus pentachloride. That is going to decompose into 2 molecules, PCl3, and 1 molecule of PCl5 is also going to decompose into a molecule of chlorine gas. So we get from each molecule of phosphorus pentachloride, we get 1 molecule of phosphorus trichloride and 1 molecule of chlorine gas. So from that we can see that at equilibrium, if we have, as we do, 0.08 moles of chlorine gas, we must also have 0.08 moles of phosphorus trichloride. We know that, and that's at equilibrium. Now, where have those 0.08 moles come from? They've come from phosphorus pentachloride. How much phosphorus pentachloride has it taken to make 0.08 moles each of phosphorus trichloride and chlorine gas? Of course, the answer is also 0.08 moles. because the one molecule of pentachloride gives us the two product molecules. Okay, so if that is the amount of phosphorus pentachloride that has decomposed at equilibrium, how much is left? That's the question. Well, we started with, let's just write down phosphorus pentachloride. We started with 0.2 moles, which I've got from the question here. We started with 0.2 moles, and we've said that 0.08 moles has decomposed, so then we're going to be left with 0.12 moles at equilibrium. So now we have, I'm going to square them in blue, now we have the moles of phosphorus pentachloride at equilibrium, we have the moles of chlorine at equilibrium, and we have the moles of phosphorus trichloride at equilibrium. But we have the moles and not the concentrations. So now the next job is to write down the concentrations. So let's do that in blue. So first of all, we might as well do PCl5. So the concentration of PCl5 at equilibrium is going to be the moles divided by the volume, you'll remember. Moles being 0.12, and volume conveniently is given to us in decimeters cubed, so we don't have to do any conversions of units there. So it's 0.12 divided by 5.00. And that works out at 0.024 moles per decimeters cubed. And let's do the same for PCl3, all right, which is going to be the same as concentration of chlorine. And for each we have 0.08 moles at equilibrium, and the volume of the container is the same, 5.00. And so that is working out to be 0.016, also moles per decimeters cubed. So now we have the three concentrations, and we can feed those numbers into the expression. So we would have 0.016 times 0.016, all divided by 0.024, and that comes out at 0.011. But let's not forget the units. So in the same way, we're going to work out the units. So we're just going to go back to the original expression for Kc and put units in there instead of numbers. So we're dealing with concentration. So we've got two concentrations on top. So we've got mole per dm cubed times mole per dm cubed for the two products, and that's over moles per dm cubed for the one reactant. And so as you can see, one will cancel out with the other, leaving just units of Kc to be mole per decimeters cubed. So let's just write that all out nice and neatly. Kc equals 0.011 from here, and the units being moles per decimeter cubed from here. QED. Okay, so let's move on now to an example where we use the equilibrium constant in order to calculate concentrations. You'll know that in the previous two examples we've done it the other way around. Okay, so here we have a reaction involving ethanoic acid, and it's reacting with ethanol at 25 degrees. When they react, they make an ester, and it was found that the equilibrium contained 2 moles per dm cubed of ethanoic acid. And notice that that's already a concentration. And also 3.5 moles per dm cubed of ethanol, the other reactant. So they're giving us concentration, so we don't have to work out that. That's quite easy. And they're also giving us the Kc. So the Kc of the equilibrium is 4 at that particular temperature. And it wants us to calculate the concentrations of the other components, i.e. the ester and water. So the first thing we should do is we should write down the expression for Kc. Okay, so Kc is going to be the concentrations in square brackets as usual of the ester times the concentration of the water, right, all divided by the concentrations of the acid times the concentration of the alcohol. There. So that's our expression, and let's see what we've got. It tells us in the equation we have the 0.2 moles of ethanoic acid. So let me just use a green pen. So we've got this one, we've got 3.5 moles per dm cubed of ethanol, so we've got this one, and it tells us that Kc is 4, so we have this expression here. So the two that we don't know are these two on top. Alright, so let's just rearrange that equation. Change to the blue color. So we're going to rearrange that expression. I usually like to rearrange first before I plug numbers in. You can do it the other way around if you like. So we're just going to multiply both sides by the concentrations of the acid and the alcohol. So you're going to get Kc times the concentration of ethanoic acid times the concentration of the alcohol, right, and that's going to equal the concentration of the ester times the concentration of the water. Okay, and now we can fit in the values. Kc we know to be 4.0. Concentration of the alcohol is the alcohol is 3.5. The wrong way around, and the concentration of the acid is 2.0. Okay, so multiply those together and you're going to get 28.0. Okay, so let's just deal with this expression here. When we look back at the balanced equation, we can see that the molar quantities of the ester are the same as the molar quantities of the water. Okay, so we can see that these are going to be equal. And so what we can then do is we can write down the fact that the CH3, C2H5, the ester, right, times the H, sorry, I just wrote that out, is this going to be the same as the concentration of the water, and they're going to both be equal to the square root of 28.0, which happens to be 5.3. And it's a concentration, so it's moles per dm cubed. So just to be clear, to answer the question, the concentration of the ester and the concentration of the water is 5.3 mole per decimeter cubed. So let's just check that our learning objectives have been met. I think we know that the equilibrium constant is calculated from equilibrium concentrations for a system at constant temperature. So I think we know that, we can tick that one. And we're also able to construct an expression for Kc with the concentrations of the products on top and the concentration of the reactants on the bottom, with the powers being the moles in the balanced equation. And we're also performing calculations either to calculate Kc from concentrations or to use Kc to work out concentrations involving that expression for Kc. We've done several of those, so I think we're good on that one too.